Hi, in this video, we want to take a look at nonlinear regression in statistics. All right, so before I talk about nonlinear regression, I want to kind of baby step some ideas here that I wanted to kind of like walk in from linear regression that we're more familiar with into nonlinear regression. So there are multiple types of regression models that we could possibly work with. And I'm going to present conceptually 4 different ones. And we will do a little bit of comparison contrast, and then we'll start digging into nonlinear regression completely. All right, so I'm going to say that there are 4 types, and this is how I personally am just partitioning it out. You can nuance it in more deeper ways. I will just leave it like this. So first and foremost, I'm going to say linear regression with all linear terms. Okay. Next one is linear regression with nonlinear terms, generalized linear models, GLMs, and then the last one will be nonlinear regression. Okay, so for linear regression, take a look at the model. Check this out. All right, so this is the formula that we're familiar with. And you'll notice that every single time I have a linear term for my predictor variables. So I have a linear term, keep on going down the list, linear term. And you'll notice there isn't a square in there. There isn't a sign of x1. There isn't a square root, anything like that. It's just the variable itself. All right, so now I'm going to say that is a linear regression model with linear terms. All right, so when we say linear regression, we don't actually mean like y equals mx plus b. That's like the college algebra version of linear. What we're talking about for this is we're talking about it's linear if I can fit my model using a matrix. All right, so if I can fit my model using a matrix, then we call it a linear model. All right, so how do we put it on a matrix? Well, a matrix is, I'm going to have a columns of variables. I'll have rows of data. Each row corresponds to a record. And if I can represent my data some way, some shape, some form in that table format, it's a linear regression format. So let's say that I have a variable x, and I think that y should equal sine of x plus epsilon. Now, that model is a linear regression model. Why is that? Well, because after I take my data x, I drop it into the sine function, then I get a vector of values from putting that in. I can put that vector onto a matrix. And so if I can transform my data so that we have columns of data, even if it's nonlinear with respect to the my original predictor variables with respect to like that college algebra linear equation point of view, that's okay for regression. All right, so here I'm going to represent linear regression with nonlinear terms is that I'm going to have y is equal to coefficients times a function, a first function on my predictor variables. Here I have beta 2, a second function on my predictor variables. I shouldn't say predictors, I should say independent variables. And I keep on going all the way out. And you'll notice that I've got a different number of columns for the prediction in this. So how I would fit this in the matrix format is that the output of this function would be one column on my matrix. This output would be one column on my matrix. This could be another column. I can just keep on going down the line. So now here, this might just be x1. This just might be x2. And that's okay. That's all right. It could be x3 squared. It could be the square root of x sub p. It could be the product of all of them. So in here, we're allowing squares. We're allowing square roots. We're allowing interaction terms. And, a lot of different ways that we could do. So there's plenty of flexibility with this. Now, generalized linear models, what we're going to do here is that we're going to extend linear regression framework to handle a response variable that does not follow the normal distribution. So remember, when we're talking about linear regression, almost always for linear regression, regular linear regression, we make the assumption that our residuals are normally distributed, mean zero, constant variance. All right, so what we're going to do is that here we're going to have a link function that connects the expected value of our target variable given our predictor variables, and then we're going to more than likely, not necessarily, but more than likely, most of the time, we're going to use maximum likelihood estimate. So it's a little bit different, but it's related. And so here we have that link function that connects to a linear equation that I can do my fitting on, and that is generalized linear models. Now, this link function, if I'm dealing with neural networks, we call them activation functions. The inverse of the link function is the activation function. The inverse of the activation function is the link function. That's the relationship. And so the link function relates the linear combination of the predictors to the mean of the response variable. And you'll notice I have G of mu. Now, the next one I want to talk about, and this is the topic of the video, is nonlinear regression. Now, here we have the most flexibility in what's going on. This is a general framework that allows for flexible modeling of complex relationships between predictors and response variables. It can capture a wide range of nonlinear patterns using various functional forms. The model can be expressed in this format. And so here I can get a much more complicated relationship between the parameters, those coefficients, than I can in the previous models that we've talked about. And so with nonlinear regression, we have a lot of flexibility, but that comes at a cost. It can take longer to fit the model. It can be harder to interpret. And it is also, if we make a bad choice on our model structure, usually it's worse in a nonlinear regression situation than having a bad model structure in regular regression. All right, so nonlinear regression is a statistical modeling technique used to analyze and describe relationships between variables when the relationship cannot be adequately represented by a linear equation. In contrast to linear regression, where the relationship between the dependent and independent variables is assumed to be linear, nonlinear regression allows for more flexibility and complex relationships to be captured. In nonlinear regression, the functional form of the relationship between the dependent variable and the independent variables is specified using a nonlinear equation or a model. This equation typically involves one or more parameters that need to be estimated from the data. The goal of nonlinear regression is to find the values of the parameters that best fit the observed data. All right, I mean, it's basically what we've been doing with linear regression all this time. All right, so the process of estimating the parameters of nonlinear regression involves minimizing the difference between the observed values and the dependent variable and the values predicted by the nonlinear model. This is typically done using an optimization algorithm that searches for a set of parameter values that minimizes the chosen objective function, such as sum of squares residuals. Now, nonlinear regression models have a lot of flexibility and can take many forms, depending on the specific relationship it's being modeled. Common examples include exponential, logarithmic, polynomial, power, and sigmoidal functions. The choice of the appropriate nonlinear model depends on the nature of the data and the underlying theory or prior knowledge about the relationship between the variables. So something that's super important in nonlinear regression is having a good idea of what the model should be for us to fit it. So nonlinear regression models are widely used in various fields, including economics, biology, engineering, and the social sciences. They provide a flexible approach to modeling complex relationships and can capture phenomena that cannot be adequately explained by linear models. Honestly, we would prefer a linear model. That theory is just so well understood. The algorithms are so built up that if I can, I'll use a linear regression model instead of nonlinear, but that's not always feasible. Now, there are some challenges with nonlinear regression. That flexibility comes at a cost. So first and foremost, estimating the parameters of nonlinear models can be computationally intensive, that it can take a long time for the computer to run it. Finding the global minimum of the objective function may not always be guaranteed. So what can happen is the true correct minimum values I could get for my data for the parameters might be a certain value, but the algorithm converges on other values. If I'm in a more complicated model, that is a possibility. Furthermore, the interpretation of the estimated parameters can be way more complicated than in linear regression, and model selection can be a challenge due to we just have so many more options with the equational forms of our models. So nonlinear regression is a statistical technique to model and analyze relationships between variables that do not follow a linear pattern. It offers flexibility in capturing complex relationships, and its application it's applicable to a lot of domains. However, it requires careful model specification, careful estimation of parameters, and careful interpretation of the results. All right, so let's take a look at an example of a nonlinear regression model. So let's say that this is our hypothesized model, that y is equal to an exponential on x. Notice that we're the coefficient in the x's. And I have another coefficient here. And the error term is outside the exponential. So that's important. This is a nonlinear regression model. There's no way for me to be able to get the parameters set up for the purpose of fitting a model using a matrix. Now, here's something that is kind of funny about it, is that if I was to, for a moment, pretend that the epsilon was equal to 0, and I took a logarithm, and then made epsilon not equal to 0 and tacked it on. So if I was to remove epsilon, take log of both sides, and then add epsilon to the outside, this equation here is a linear regression model. All right, so here I can put this logarithm of y as a column, as a vector. I can put a column of ones for the intercept. I can put my x data as a column. And so in this format, I can actually run linear regression, even though from a college algebra point of view, this is not a linear equation because I've got a log in there. All right, so the first equation is not a linear regression model because there's no way for me to get the coefficients separated and have epsilon in the right position. The second one is a linear regression model. All right, so now the difference between linear regression and nonlinear regression. In statistics, the term linear regression refers to a model a framework that can accommodate both linear and nonlinear relationships between variables, as long as the model can be expressed using matrix equations. This may seem counterintuitive, as the name linear regression suggests like a college algebra linear aspect. However, the linearity in linear regression refers to the parameters of the model rather than the variables themselves. As in linear regression model, the relationship between the dependent variable and the independent variables is expressed as a linear combination of the variables, where the coefficients, that is the parameters, are multiplied by the independent variables. The model can be represented using a matrix equation of this form. If I can somehow, some way, some shape, some form, get this equation written down for what I've got going on, I can use linear regression. And that's what I would prefer to do. The linearity in linear regression refers to the parameters. I want to emphasize that. The model can accommodate nonlinear relationships between the variables by introducing nonlinear transformations of independent variables in the model, as long as I can get it onto that matrix format. For example, if the relationship between a variable is better described by a quadratic function, the model can include a quadratic term such as x squared as an additional independent variable. By doing so, the model becomes linear with respect to the parameters. The nonlinear relationship between the variables is effectively captured through the linear combination of the transformed variables and the associated parameters. The estimation of parameters in linear regression is performed using methods such as ordinary least squares, which minimizes the sum of squares residuals. It's important to note that while linear regression can handle nonlinear relationships in this manner, it's still subjected to these assumptions. We must still have these assumptions. First one is the linearity relationship. So this is saying that my model structure is correct. In linear regression, I need to have independence between observations. We have to have constant variance of our residuals with respect to our predictor variables. And we need to have normality of the residuals, where we have mean zero and then that constant variance aspect. If these assumptions are violated to a significant extent, the model may not provide accurate or reliable results. In such cases, alternative regression techniques such as nonlinear regression or generalized linear models may be more appropriate. In general, we're going to want to use, it's preferable that I would use linear regression with all linear terms. If I can't do that, my next choice will be linear regression with nonlinear terms. After that would be a generalized linear model. And if that still doesn't work out, now let's start talking about using nonlinear regression. And so that's like, in my opinion, the order in which we should try to build our models. Doesn't always work out the way we want to. Nonlinear regression is a tool in our tool belt. All right, so let's look at an example of linear regression with nonlinear terms. And so here y is equal to beta sub 0, which is our intercept, plus these terms here. Now you'll notice I've got a linear term on x, linear term on x2. I have a quadratic on x1. I have a quadratic on x sub 2. All right, so this is nonlinear with respect to my two predictor variables, but this is a linear equation for the purpose of linear regression because the parameters have a linear relationship between the predictors. I can put this onto a matrix equation and I can fit it nicely. All right, so now let's compare generalized linear regression to nonlinear regression. Generalized linear regression and nonlinear regression are two very distinct statistical modeling techniques with different underlying assumptions and applications. Here's a comparison between the two. So the relationship between the variables. Generalized linear regression, here this assumes a linear relationship between the predictors and the link function that relates to the predictors to the mean of the response variable. However, the response variable can follow a non-normal distribution. With nonlinear regression, it allows for a flexible modeling of the relationship between the predictors and the response variables with no specific linearity assumption. Nonlinear regression models can take various forms, including exponential, logarithmic, polynomial, power, and sigmoidal functions. Now, for model specification, GLMs, it requires the specification of a distribution family and a link function. The choice of the distribution depends on the nature of the response variable, whether that's Gaussian, binomial, Poisson, etc. For nonlinear regression, it involves specifying a functional form for the relationship between the predictors and the response variable, typically involving one or more parameters that need to be estimated. The choice of the functional form depends on the specific relationship being modeled and the underlying theory. For parameter estimation, GLMs, the parameter in generalized linear regression are estimated using maximum likelihood estimation or other related methods. For nonlinear regression, parameters are typically fitted using ordinary least squares and using an optimization algorithm. Now, for assumptions, generalized linear models assumes that the errors or residuals follow a very specific distribution within the chosen family. Additionally, GLMs assume that the relationship between the predictors and the response variable is captured by the link function. Nonlinear regression assumes that the functional form chosen by the model and the relationship between the predictors and the response variable is appropriate. Notice that it just says appropriate. It's very vague. It's not nailed down there. It's just saying that we got it right when we picked our model form. It may also assume that the errors or residuals are normally distributed and satisfy other assumptions similar to linear regression. Now, for applications, GLM is commonly used for modeling binary outcomes such as logistic regression, count data, Poisson regression, time to event data, and other response variables that do not follow a normal distribution. Nonlinear regression, it's often used when the relationship between the predictor and response variables cannot be adequately represented by a linear equation and requires more flexibility and a more complex functional form. All right, so now let's go ahead and actually do some modeling using R. So what we're going to do, we're going to use the MT cars data set. I want miles per gallon to depend on the weight of the vehicle. All right, and here we have a coefficient and an exponent as my parameters. Now, something about this is that for us to get our estimate, we need to give initial values for our estimates. And these in a very complicated model structure, that starting value is critically important for a very complicated model. If it's a simpler model, it's not going to be such a big deal. But we really want to have it like in the right ballpark. So if I don't know these values, something I could do a grid search on my model, plugging in the A and B values to figure out what looks like a reasonable initial guess. And so here, it's very nice that if I run the summary function, it will go ahead and give me hypothesis testing on the parameters. And something that is important to know, I've never seen this written down, but from experience, if it takes a long time, a lot of iterations for your model to converge, that's a sign that you have a bad model data combination, that there might be a problem with it. So if it's taking a long time to converge, if it takes a long time to get through iterations, that's a sign that maybe you want to try a different model structure. Now, the NLS function is in base R, the workhorse of nonlinear regression. And so the parameters that we have to enter into the function, the fundamental ones, are the formula, the data, and our initial guess at the values. Once we have our model, we can use the summary function to do our hypothesis testing. We can use the coefficient model to get the parameters out. Now, they may not be technically coefficients, but depending on the functional form of the model, but it's the same function to return the parameters. We can use the predict function to get the predicted values for our training data or a new data set. We can get our residuals on the training data, and we can plot the diagnostics. Now, there are some severe difficulties in nonlinear regression. These difficulties are why I advise you to avoid this technique if you can. Sometimes it's just the right way to go. Sometimes your stakeholders want it, and we just do it. So non-convex optimization, what this is saying is that it's possible that the algorithm will give me a result that looks like it's a minimum, but it's not. And I won't really know it, or if I find out, I won't know it until it's too late. So non-convex optimization, I could be in the situation where, let's say that these two values here in higher dimensional space look like they are minimums. So if my algorithm converges over here, it didn't reach the true minimum. The true minimum is over here. If it reaches over here instead, then I'm going to have the actual true minimum. And so how do we protect ourselves from this? First and foremost, by understanding the mathematical equation that we're using for our formula, and then also maybe doing a grid search to just find what looks possible. And then when I find a region that looks lower on my optimization function, then I'll use NLS. Now, my initial parameter values, if I choose these poorly and there's multiple local minima, then this can shoot me over off to something that just doesn't work out. It's also technically possible that the initial parameter values could shoot me off towards infinity. That could be a problem. So multicollinearity. So I have, correlation in a higher dimensional sense between predictor variables, just like regular linear regression. Model specification. I made a mistake in declaring what my model is. Same risk in linear regression. And computational complexity, here it can be demanding on the computer to fit a nonlinear model. And so, you can hit the run button and you can leave and you come back to work the next day and it's still running. So this is just something to be mindful of if you're going to go this route. Now, the assumptions could also be violated. This is another risk, just like with regular linear regression. And model interpretation for nonlinear regression can be much more difficult than it can be for linear regression. The most important thing in this type of modeling is to have the right functional form. If I have the right functional form, I'm as set up for success as I can be. Now let's look at a non-convex nonlinear regression situation. So let's say that y is equal to 2 times x plus some noise. All right, so 2 times x, I've got a curve going there. So when I go to fit, when I try to find a minima, it could be kind of difficult on there. And so let's say that I have this model. This is a true relationship, and I'm trying to fit this one. So I've got an A, a B, and a C. So now, if I look at the original model, really I want an A. The perfect model will be A is equal to 2, B is equal to 1, C is equal to 0. So really, I could drop B and C from this fitting, but we're pretending I'm in the situation. I think that there needs to be an A, there needs to be a B, and there needs to be a C. In reality, I don't need B, I don't need C. And so if I have more parameters than I really need, this can make it harder to detect what's going on. All right, so now let's go ahead and fit our model. So here is our nonlinear function. This is a custom function that we built up here. Here are my initial guess values for A, B, and C. So I can improve this by A equals 2, C equals 0. And then after it's done fitting, we can see that I did a pretty good job of fitting the model. All right. All right, so nonlinear regression, it's fun to play with. It's fun to have that flexibility. I recommend that you avoid it if you can, but sometimes we don't have a choice. Sometimes, fitting models gets dirty. Sometimes, our stakeholders want very specific things. If you're in that situation, go for it. Do what you need to do to get done. Well, that's all I've got for you. Life is short. Do math.